or maybe here. So there have been a number of technical advances with CT that have made it better for cardiac imaging. The first was back in the 80s. This is when I first got into imaging research. I started grad school right around here. The number of CT scans in the millions, we're about 10 million here. A scanner actually comprised a single detector row and an X-ray source, and you spiraled that single detector row around the patient. So it took a lot of time to take an image. It took many, many slices to make an image. And so what the reason was the electronics for the detectors and the power going into the X-ray source all came in on ribbon cables. And so you had cables attached to the gantry. And so when the gantry rotated, you couldn't just keep rotating because the cables would get all twisted up and break. So you had to rotate one direction and then rotate in the opposite direction, right? And so basically, it was a very slow process. Siemens made a big jump in transferring a technology from other fields to CT, where they came up with a slip ring technology, which was the electrodes that are transferring power to both the X-ray source and getting signal back from the detectors. Those electrodes were essentially brushes that were on a track around the gantry. And so you had maybe 16 parallel tracks and brushes. And so all of the electronic signals went through those brushes. And given that, you could just rotate in the same direction continuously. And so that made it much more efficient. You didn't have to rotate one direction, come back. And so when that innovation came in, the usage of CT went up in the 1990s because you basically could scan so much faster. And then at the end of the 1990s, CT manufacturers thought, well, I have this single line of detectors, X-ray detectors, that's going around a patient. Perhaps I should just put two of them in parallel. And now I have two samples or two lines sampled simultaneously. So I cut my scan time by a factor of 2 just with that addition of that one extra slice, right? Well, then I can go to, say, 4, double it again, and now I have 4. So I've cut my sample time by a factor of 4. And basically, multi-slice CT started. And as the number of slices went up, the usage of the imaging modality went up with it. Until finally here around 2008, we're looking at 70 million CTs a year in the US. And it has just continued to go up. So here's the idea. You have, instead of one detector, which was our initial configuration, we have 4. And it went all the way up to Toshiba introducing a 320 slice CT scanner that had 320 detectors in this direction, in the Z direction. GE, its scanner has 256 slices. Toshiba has become Canon. They were purchased by Canon. They still have a 320. And Siemens has always kept their detector array in the Z direction much shorter than the other vendors. Siemens enjoys doing this helical scanning, so they don't mind doing a spiral around the patient. And so their detector size in this direction is usually about 4 centimeters or something. So it's in the central part, and then they'll move that across the heart. Okay. So here's our geometry now. In a modern scanner, we have an X-ray source up here. We have slices in the Z direction, or detectors that are divided in the Z direction, and then detectors along the arc of the gantry. So looking at where the isocenter is, our maximum field of view is whatever the X-rays can intersect and then hit the detector. So this angle down here is usually about 45 to 55 degrees of detector down here. We can put our patient in the center of the scanner. and measure a field of view. The maximum you usually get is about 45 to 50 centimeters in that direction. So the whole thing rotates, the source and the gantry in most CT scanners rotate together. There's one exception to this, and this was a scanner that was actually invented in the was invented in the 70s, was brought out commercially in the late 70s, early 80s. And it's called an Imatron scanner. And it was a really cool innovation in that we had a ring here. It's a target. It's a metal tungsten target. And what happens when an electron hits that target, X-rays shoot off. And that's how it's done in an X-ray tube. So this scanner is like a giant X-ray tube where you have a ring around here that's a target, and you have an electron beam that you steer with magnets. And steering an electron beam is just like old-time TV, where you basically had an electron tube in the back of your TV, and magnets used to spray an image across a phosphor screen onto your television. And so it's that same technology, except this electron tube makes a lot more electrons. And it's almost like a small linear accelerator for electrons. But what happens is you get this beam, and I can steer it with magnets here such that it hits the target, but I can sweep it across this target. So it's kind of like rotating an electron source, an X-ray source, I should say. The electrons hit this, X-rays come off. So I get an X-ray source that rotates around the patient. And so I can make the rate of rotation as fast as I can sweep those electrons across the target. And so that's milliseconds, basically, right? This sort of, I get images in 30 milliseconds or something. And here's the data acquisition system back here. So basically you have a point target, you acquire beams from that point target, and you move the point target around. Now, this has limitations. The slice thickness it only went down to a certain thickness, and then they couldn't really make it any thinner. So the slices are kind of limited to 2 millimeters, 3 millimeters thick, which nowadays, as we'll see, is pretty low resolution. But many of these were sold, and they were sold ostensibly to measure coronary calcium in patients because you could do cardiac scanning, whereas on the older CT scanners, you really couldn't do cardiac scanning. So one of the other aspects of the geometry of the engineering is here's our X-ray tube, right? It has an electron gun. The electrons hit a target, and then X-rays fly off the target. It's a funny little diagram. I don't know why it looks like an inverted ice cream cone, but anyway, essentially the X-rays are coming out like this. And what is happening here is this black signal here is called a bow tie filter. And it absorbs X-rays where it's thick, and it lets X-rays through where it's thin. And so this will cause a lot of the X-rays that are coming out peripherally to get absorbed before they go through the patient, if they're going to go out here through the patient. And the ones down the center line, we have a higher flux of electrons coming down the center line. A couple of reasons for this. One, the patient is usually the thickest through this center line. So if we want a decent number of X-rays to be detected on our detector, we need a higher amplitude or a higher intensity of X-ray beam going through this thick part of the sample versus on a trajectory over here through the thinner part of the sample. Also, if I'm detecting things way out here that don't hit anything, just hit air, and then they're on my detector, I have orders of magnitude more photons to detect over here than I do here. And it gives me a dynamic range problem. So I need to detect millions of photons off to the edges and 12 photons maybe down the middle, right? So that basically dynamic range was an engineering problem for a while. So you put in this known shape, and it will, if there's just air here, it will make an image of that shape. and you can normalize to that, right? So we'll see how that works. So there's many different bow tie filters. Here's a small one. So if you have a very small field of view, you're interested in imaging, like say the torso of a small child or an adult head, you can use this smaller bow tie filter, and then a medium and a large. So the large is if you need a full body scan of somebody who's pretty large, right? We wrote a paper about, I guess, 5 years ago now, maybe more, where you can always use the small filter for cardiac. Even though you have the rest of the torso, the thing you're really interested in is the heart. And so it doesn't really matter about the image quality out in the rest of the torso. What matters is the image quality around the heart. And so you can cut your dose by a factor of about 2 just by using a head bow tie filter and just looking at the heart. And so, here's an example. If you basically, so here's a clinical image. Here's an image where we've filtered out a lot of peripheral photons and just looking at the heart, and you can see there's a lot more noise in constructing the peripheral image. Here's the absolute difference between those two images. And then here, so this is the body bow tie. This is the heart-centered bow tie. So you see there's a lot more noise out in the periphery, but you don't really care. That noise isn't crossing across the heart. And here's the dose reduction field. So there's no dose reduction to the heart, but there is a lot of dose reduction out to the rest of the patient. So essentially focusing photons and dose where you need it. So here's a diagram showing the path or the line that photons would go through a patient. So if my source is here, photons are coming down through these lines, and they enter the patient here and go through the lung and then the patient's back, and they may be absorbed or not absorbed. If they are not absorbed, they hit the detector here. Okay? So we're essentially making a shadow on this detector. And I have a straight line for each photon path from the source to the detector. Now remember, in SPECT, it can happen that a photon comes through, hits something in the patient, and goes off at a different angle and comes out to the wrong detector. So we still need to get rid of those photons using essentially an anti-scatter grid above this detector. Okay. Let's take a look at what the shadow looks like. So my pathway of a photon coming through here, I have to get on this pathway, I have to get through a big chunk of bone right here, which is the sternum. That's on the front of your chest. You have a big bone plate there. And then it goes through the heart, which probably has contrast agent in the blood, so a lot of photons are absorbed. Then it goes through the aorta, perhaps here, is through the aorta, which would have contrast in it, through the spine, which has a lot of bone, and then through the back. And then it comes down and hits the detector. As you can see, not many photons make it through. So the X-ray intensity at the detector is quite low here because they're all getting attenuated by the body. Whereas for this detector here, if I go back to the source, it goes through soft tissue, might go through a rib, but then it goes through lung, which is essentially air. So not many photons are attenuated there, and then through the back. So I get a high number of photons at that point. If I plot the number of photons I see or the X-ray intensity as a function of position along this detector, this is what the function looks like. So this is detector number from detector 1 through, say, 1000 here. And then I get this thing, which is a profile, okay, of the X-ray attenuation for that patient with the source at that position. Then I repeat that measurement at a different angle. So I get a new profile, given that the source has moved to a different angle and the detector is rotated around with it. And now you can see this big dip where we had essentially where we're going through the spine down here is hitting at this location, right? So we have that big dip has moved over here. So we're going to get a bunch of these angles, right? And remember, in SPECT, we had the whole camera sitting there for about a minute or 30 seconds, and then we clicked the whole camera to a new angle. In CT, we just get that thing rotating, and we go through these angles, A through B. Well, we just take data as we're moving through these angles. So we have approximately 1,000 detectors over here, usually around 800, something like that, or 900 detectors over here. How many angles do we need? Or how many angles should we take to make a nice picture? Is a good question, right? 50? 200? 2,000? 10,000? I don't know. How many, who's going to take a guess? How many angles should we take? Order of magnitude, 10, 100, 1,000, 10,000. 100? Yeah, that's a good guess. It's close. It's about 1,000. Yeah, because I got 1,000 detectors, right? So basically, I can click that gantry one detector position, take another picture, click it one, take another picture, click, 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 right? That's the way it's done, though, is the X-rays are on continuously. So we don't flash the X-rays. We put them on continuously and we just collect data as we go. So there's a couple of ways to do it in Z or in the slice direction. The first way is we have that geometry we just looked at, and we'll do one rotation around, and we'll take all of that data, and then we'll move the patient through this ring, and we'll do it again. And so we'll just stepwise go through the different slices in basically the superior to inferior direction or the head to foot direction. The spiral scan or helical scan is a different approach, and that is we keep this thing rotating all the time and just continuously push the patient through as the detector and source is rotating. This one you stop. This is called step and shoot. So we take a step, shoot an image, step, shoot an image. This is called helical or spiral, so it's continuous acquisition. And you can imagine we can move, it gives us another degree of freedom. We can move the patient through here at different speeds. So how fast should we move the patient through here? It obviously has something to do with how fast a rotation occurs, because we do 360 degrees, but the whole patient has gone through here, then that data will be sort of spread out over the whole patient, right? At 360 degrees. So we need to look at the distance we move per revolution, right, which is D, divided by whatever the beam width is here. So if it's a really thick beam in Z, we can push this faster. Okay? But we'd like to paint the entire patient. We don't want big gaps in that paint. Although some manufacturers push that, and they will have gaps there, and they'll interpolate. And Siemens does that especially, and they call it, I forget what they call it, turbo or something. It's probably called turbo. So in terms of speed, looking back at how CT images were initially taken, which was like you click around really slowly on the angle, and then this only goes up to 2008, but the number of pixels per second that are acquired with CT, this is the growth over those 35 years or something. And the black curve is just Moore's law, right? You guys know what Moore's law is, right? Just how many transistors you can pack on a chip. So it's basically governed by the electronics principally of the system. So back here in 20 minutes, we got two 80 by 80 images. Here in the modern scanner, in essentially half of this time, it rotates, once. You can make an image without doing a 360-degree rotation. And they now rotate once every 250 milliseconds or so. And with the Toshiba, you have 320 slices. So you get 320 512 by 512 images in like 150 milliseconds. So it's a lot faster, right? It's pretty cool, right? So here's the gantry rotating. That's, up to speed. This gantry goes, I think ours goes 230 milliseconds, or something like that, 240 milliseconds for 360 degrees. And you look inside, and this is the detector. This is the size of the detector in Z is quite wide, right? So along this way, it's 16, at the center, it's 16 centimeters. Let me go back to here. So along this way, right, we have about 1,000 detector elements. In this scanner, it's like 800 and change. Along this way is the slice direction. The patient's head is over here, their feet down here, or vice versa. And so on this scanner, there's 256 elements in the detector on this direction. So it's 256 by, I think it's 832 it's like a digital camera with that as its array, right? Which is pretty small when you think about how the array in your phone, right? What's the array in your phone? Anybody know? Top of their head? Say again? It is called megapixel because there's millions of pixels on that array, right? And most of the time nowadays it's 12 megapixels, which is 3,000 by 4,000 detector elements on the array inside your little camera, right? So this is a very low number for that, but this is an X-ray camera, so it makes it slightly special, right? So this is what it looks like when they installed ours in the hospital over there. And this is the power supply, the X-ray tube. This whole gantry rotates around very quickly. It does create a lot of wind and it creates a lot of noise if you don't really focus on the engineering to try and make this thing rotate fast and quietly. That's why the companies that do this successfully are companies like Philips, Siemens, General Electric, Canon. They're people who've built things like jet engines and huge motors and things like that, right? So mechanically, they're very stable. Um, Up here, like when this thing's going, when it's rotating, ours goes at 4 cycles per second now. And this chunk of hardware out here is at 60 centimeters. It's under an acceleration of about 40 to 50 Gs. So 40 to 50 Gs, if you're in a plane and you pull 40 Gs, you just black out. You're not coming back, right? So it's a very strong force. And so all of these things are buckled down really, really well. This is what one detector element looks like. I think I might have, can I leave here? Yeah. Let me go out here. I think I brought up a movie. I don't see it here though. No, I don't want to do that. Damn. I thought I had it up. Let me see if I can get here it is. Mhm. Oh, there it is. Good. So here's the principal components of this thing are if we pause this for a second, go back to where it's clear. So we have the power supply. this creates a high voltage for the creation of the X-rays. So remember, our X-ray energies are between 40 kilo electron volts and 140 keV. Think back to SPECT, we had photons of 140 keV we needed to detect. Here we're making photons with an X-ray tube at 140 keV, all the way down to about 40. We filter out the low ones, the low energy, because they don't get through the patient, so you don't want to put them in the patient. So normally we're looking at an average energy of about 75 keV. And that voltage is created by this big old thing. And I'll get rid of this. I know. And here's the X-ray tube up here. We just got a new X-ray tube that gets up to 120 kilowatts or something and 1300 milliamps. And so the whole thing rotates together. Here's the detector down here. You can see it's about, I don't know, 45 degrees, something like that. So it starts rotating, get up. And now here's the X-rays being generated while the thing's rotating. And the interesting thing about that is you saw there were two colors of X-rays, right? There's a green and a blue. Ticka, 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 ticka. This X-ray tube is really interesting in that it can flicker between two energies. So it can give you a brief pulse that's at 70 keV is the peak X-ray coming out of there, the highest energy X-ray. And then it'll flip to another mode and produce an X-ray beam where the peak X-ray energy is 140 keV. And it can flicker back and forth between those in sort of kilohertz range, like every 2,000 times a second, which is pretty unusual. They're the only company that does this. And the reason they do it is to flicker back and forth like that, they'll make two pictures. One picture will be made from the low energy X-ray bath or a source, and then we'll make a picture with a high energy X-ray one. And those two pictures will be slightly different because tissues absorb X-rays at different energies differently, right? So basically, soft tissue versus iodine versus calcium, etc., they will absorb X-rays differently at 140 keV than they will at 70. So you get a two-dimensional image, right? Each pixel has two dimensions. And that's called multi-energy CT, or sometimes dual energy CT. Let's move ahead on this. So here we're going to explode the detector. This is pretty cool, actually. So they explode out the detector, and here are the detector elements. That little chip there. Oh, you little bastard. Sorry. It took away my control of the screen. Sorry, I didn't. There we go. Okay. So here's the chip. There's the detector. Okay. This is an anti-scatter grid. Here are the detector elements down here. And this whole unit is going to get dropped in here. There's about 13 of these units across the detector element. And then we'll open that up. So here's we're taking the, essentially the anti-scatter grid off the top there. And then we'll pull out one of these chips. Okay, and you can see there's a grid, an array of little detector elements on each chip. There's like 32 of them this way, 16 this way. And they're just put in here as modules, right? And inside each module, you get a connector that goes back to their own preamps. And this is the crystal that's in one of those chips. They have this GSI crystal, which has a very short flash, very quick flash, so they can scan this flickering energy quickly. Okay, so that's the detector array. And then the anti-scatter grid, here you can see, you know, X-rays coming down straight are going to go through and hit the detector and make a flash. Those coming at angles will not. And they try and isolate detectors from their surroundings, you know, with those septa between them. So it's pretty cool, heavy industry kind of technology. Hard to make one of these in your lab, right? So of this nature. And then here's that flicker where the green is low and the blue is high or something. And you're getting those two pictures. Okay. Go back to PowerPoint. Okay. So this is the material, gadolinium oxysulfide. So it's this, and it's basically doped with these elements to make this characteristic flash on the detector. And the deal with this is if you have this detector, basically the decay time is 30 to 50 nanoseconds. So the flash comes up and then it's gone in tens of nanoseconds, whereas these are, 100 times slower, right? Or 1,000 times slower. And so they have a delay or afterglow. And so you can't go as fast. You can't sample as fast. Okay. If we image air with the scanner, so basically I don't put anything in the scanner and I just take an image and then go to the raw data file. And this took probably 4 days of hacking, but to the raw data file and then figuring out how they store the raw data in that file and bringing it up as an image of essentially the X-ray intensity at each detector element. So this is zoomed in. This will be the center of, this would be that one right down the middle. And then as we go to the edge of the detector, and then this is the Z direction here. Okay. And you can see when you're imaging air, the X-ray intensity is not uniform on the detector, right? You would assume it would be if the intensity from your X-ray source was uniform. It would illuminate this thing uniformly. However, a number of things are at play here. One, as we move away from the center, remember the bow tie filter? Well, the bow tie filter's on here. And so the number of X-rays just drops away with radial positioner as we go out from that bow tie filter. There's also an interesting dependence on the Z direction. Like it's brighter on this part of the detector than it is on this part of the detector. And remember, this grid is fixed in its orientation with respect to the X-ray source. They're going together. So this pattern, this non-uniformity pattern, this is going to roll with the whole thing. It's not because the table or something is in a different position. So what this is, it's called the heel effect. And the number of X-rays that can get to the detector over here is higher than those over here. Okay, and so there's this gradient across in Z, and I think oh, here it is, good. So up above us, so where I'm looking at this, I'm looking down at the detector. So it's like I'm the X-ray source. So in this drawing here, the electrons come in and hit the X-ray source, which causes X-rays to come out. That's how we make X-rays. Down here is the patient and the detector, everything. So the electrons come out here, hit the source. Those, essentially those detector elements that are right below this angled anode, the X-rays have to go through more material to get out of the target, right? And so what happens is the ones at IA, which are these ones up here, fewer photons get out than the photons that go forward because there's a shorter distance to get out of the detector, right? And so here it looks really bright because these X-rays have not had to go through that much material. So that's called the heel effect, okay? It's not that important that you remember this. What is important is that this picture is not uniform, right? So when you take your raw data for a CT scan, you need to take into account that a picture of air, which should be a uniform picture, everything uniform, has this as its raw data. So we need to take care of this, right? And so the way it's taken care of, and it's a bit of a mess, is every day when the techs get to the scanner, they put in a special phantom and then they also take images of air. And those are called the air scans for that day. And then they put in a water phantom and they get a water scan to get exactly how many photons get absorbed by the water, right? And we'll see why. So in the raw data, when I have raw data from an imaging a patient, when I download that raw data, I get the raw counts as a function of angle, but included in that file is an air scan, right? So if I have to reconstruct this a year from now, I get the air scan that happened on the day that this patient was acquired, right? Which is a little bit, uh, it's ad hoc, right? It's like, how are we going to fix this? Yeah, it's a calibration. That's exactly what it is. You calibrate the scanner every morning, right? And now, so we looked at heel effect. That's this bright spot. We looked at why this gets dark because it's the bow tie filter. But look at each set of detectors, right? What the heck's going on there? There's these little squares. It's almost like when you fly across some of the western states at the right time of year, you see these different crops in different fields and always rectangular crops, right? Really neatly done. So it's like flying over Kansas. You look, there's fences, and then they're doing spinach down here, and they're doing, potatoes over here. So what's going on here is probably this group of detector elements. Remember, it's 32 this way, 16 this way. So this is like 8 by 8. That little group of 8 by 8 probably has one preamp. And its gain is probably a little different than the other preamps around it, right? So you try and get all those together, but you can only do so well, right? And this can be a very small percentage, but when we're looking at an air scan, it shows up because we can really hone in and look at accurately what the differences are between these things. Okay, so we have to take this into account as well. I would say this is a guess. The manufacturer won't tell you. They're not going to tell you, right? They don't want you messing around in their raw data. And that's because normally a manufacturer, as you've seen, there's all of these calibration and fixes. They don't want you to know about all of the fixes, right? So they'll take some engineering decision which will cause some data issue, but they'll fix it later, right? But they don't want you to know about that, right? CT is a very interesting business. Very few academic labs get access to the internal white paper that would tell you what's going on here. They just don't do it. And a lot of stuff like this, they don't patent. It's internal trade secrets so that they don't have to release how they're actually doing certain normalizations and stuff like that. So you have to be really good at hacking, right? If you want to use your own raw data, right? Unlike MR, in MR, they have big manuals they give customers. They will fly customers to the factory. Like GE, I did this, I don't know how many times, to Wisconsin. And you sit in a classroom like this, and they teach you how to program the scanner, and they teach you the file structure, and they teach you all of the tricks underneath. MR grew up in essentially universities, right? And that's why it's a wide open space, right? CT, not so much. Every manufacturer's scanner is different, and they've taken different tracks, to do dual energy, et cetera. And I've told you this before, I think, there's a meeting called the CT meeting where everybody who knows how to do CT gets together every other year. So it's every 2 years, and 270 people show up. And that's it. For the whole world, that's how many people know how to do CT, right? Like really know how to do CT and know what's in the manufacturer, because half the people there are from manufacturers, right? Whereas the International Society of Magnetic Resonance in Medicine, ISMRM, 6,000 people go to that meeting, right? So it's a huge academic force driving innovation in MRI. In CT, I would say it's only companies driving innovation, a little bit in academia, but not much. So if you want an academic career and you're young, I would say go into MR, right? When you get old and it doesn't matter as much, then you can go into CT. Right. So here's I don't know, is this going to play? Yeah. This is looking at the anti-scatter grid from above. So you can see here, there's a little ball down there underneath the anti-scatter grid. We'll go down, we'll look at it. There it is right there. So these things are just sitting on a light box. And then we go up above and look at it through the anti-scatter grid. And you can see at a specific angle, I can see the shadow really well. If these were X-rays at different angles, it would just disappear. The reason it doesn't disappear is because it's light. And so you're getting reflections inside the thing. But there's only really one angle at which you really get the best shot of that. And it's both in this direction, which is the theta direction, and in this direction, which is the Z direction, right? The slice direction. So this scanner is interesting in that it has this big, fat slice, 256 detectors, and it's 16 centimeters thick. It's huge, right? And Siemens would argue that off to the edges, this thing is really distorted, and you shouldn't use that data. GE says, look, off to the edges, we know how to fix the data such that we can use it. So they do use it. So here's an example of a phantom that we made. We printed this sort of cycloid thing. There's contrast in the middle. It's like a sine wave. And then this is the cap. The contrast is in the cap. And then we're looking at it from different angles. Oops, my bad. Right. And so these things are cardiac leads, pacing leads that you would see in a heart. And this experiment was designed to try and minimize the artifacts from the leads. And so this is what it looks like in 3D as we rotate around that phantom. The reason I'm showing you this is because this is what the raw data looks like. So here's my full detector. Okay, so it's 16 centimeters this way, 256 points, about 800 and change points this way, which is the detector direction or the theta direction. Okay. And then as I turn that on, these are the different angle views that I'm looking at. So remember I said we're going to take about 1,000. This is those 1,000 views. Oh, there's something special happened. We go back here, we're looking just at the right angle. The drop off as we go out here is from the bow tie, right? As we get outside. And then we have this bright signal here. You can see there's still a slight contrast where you had those detector elements, but the dynamic range of this signal is much bigger than the raw data I showed you. I squeezed it down so that we're looking at the details. Here, we've got a really dark thing, which is the lead. This is dark because there's a lot of contrast here, right? And then that's what it looks like from different views. Right? So we're going to use all these views to create that three-dimensional picture. So if I look at one detector element, let's take a look at this one here. Say I'm sitting right here and ask, what is the intensity or the flux of X-rays hitting that detector D? Okay, so D is going to go from 1 to, I don't know, whatever 256 times 1,000 is. And well, 256,000 Ds I have. So I'm going to look at this D right here. So I take the flux I would measure if I was just imaging air. And we remember this morning took that number, so we know this number. It's in the database. And then it's not going to be that unless there's air. What I do is I drive through the patient or the phantom here, and whatever I hit has a linear attenuation coefficient, which is, how the signal is reduced, right? Or the probability of absorption. And I do the line integral from my source to my detector of those linear attenuation coefficients. They're dependent on energy, but we're just going to evaluate them at the average energy of the beam, right? And so I attenuate this I naught times this number, which is somewhere between 0 and 1, right? This number is, right? And that will give me how many X-rays I see at my detector. This is what it looks like in a human, right? So now we've got projections through a human chest, right? You can see the spine there's the spine right there, right? This is the heart with contrast in it right here. This dome here is basically the liver right there that everything's resting upon. And we're just taking different shots at different angles, okay? If we look at that equation from the last slide, what I can do is I can take I naught and just divide ID by I naught, right? So that's going to be a number between 0 and 1, because ID is going to be smaller than I naught. Something gets absorbed, okay? So we'll do that. We'll divide. We'll take the logarithm of both sides of the equation. That gets rid of the exponential, all right? So now I just have, I'm going to put a negative sign here for convenience, just to get the sign right, because this is between 0 and 1. And then essentially I have a real number that is equal to the line integral of the attenuation coefficients through the pathway that X-ray took to get to the detector, which is really cool, right? So now I've just got a real number, and I've got this integral. My X-ray CT image is going to be an image of these things, of mu at each position. And so that's how we're going to solve for those things. This is just essentially if you wrote out the integral as a discrete sum, right, through the pathway, through voxels, you just get a set of equations that you have to solve. The complications that can occur are obviously if the patient isn't holding their breath, or over time they're breathing and their diaphragm's moving up and down. So this is over 27 heartbeats. This is how much motion. When you don't tell a patient to hold their breath, this is what it looks like. It goes up and down. Sorry that the grayscale is screwing up. That's something to do with PowerPoint. But you can see there's a lot of motion, right? Here, this is continuous acquisition. So what we're doing here is exceedingly low dose projection imaging, where we spin the gantry around and we take one projection every time the gantry comes back to the same position. So it's just like boom, boom, but it's just one shot of X-rays. We don't take X-rays any other time. Super low dose, but these frames are separated by 230 milliseconds. So there's like 4 frames a second. And so that's what a breathing patient looks like, right? Which, should give you pause if you're doing SPECT. Something like that's moving a lot, right? It's like centimeters it's moving. Yeah. So you do want to take this into account. And so in CT, because we can now image so quickly, you just ask the patient to hold their breath. And they can hold their breath usually for 10 seconds without any issues. And so you stop this motion and then you take the picture. And then the picture that comes out looks something like this, although this picture, I was just looking at the date this morning. This is from 2014, so that's like 12 years ago. But it still looks pretty good, right? So here's a right coronary artery going down this way. left coronary artery at the top of the heart here. Let's go back up to the top. Aorta, ascending aorta, and then a big vessel right here. This is called the left main coming off the aorta. And we can follow that out. Here it is here. And then one branch is going to turn and go this way. Another branch is going to go behind the heart this way. And we can watch that happen. There it goes. One's down here. And then these little bright signals inside the vessel, that's calcium. So that thing there, that little dot, is a chunk of calcium in that vessel, indicating that this person has had some kind of vascular inflammation or something occur there and then repair with fibrotic tissue. And when that repair is occurring, calcium shows up. You actually build bone for some reason. So that's like a history of cardiac disease. So here you can see all of these dots here are also calcium inside that vessel. And then one of the big knocks against CT is like, if I get to this slice and ask the question, is that coronary even open? You've got so much signal here from so bright from the calcium, it gets in the way. That's called calcium blooming. Physicians come up with great names for technical term. It's actually just blurring, but it's, you know, physically and from an engineering standpoint, you're just blurring that really bright signal. But they called it blooming. It's much more romantic. And so anyway, to get rid of calcium blooming is a big goal in coronary CT, because as you can see, it really interferes with the signal in the vessel. Say that again, I'm sorry. This? Oh, that'd be the spine, I think. Like if we go through slices, that's the spine, right? Different vertebrae. This is the descending aorta. Okay, so there's a big pipe that goes in an arc from down it goes. That's the descending aorta. This is the aortic valve leaflets. And if we go up high, you can see some nice imaging of the calcium on the leaflets. We go up higher. This is the ascending aorta. If you make a movie of this over the heart cycle, you will see in a younger person that the aorta and the large vessels, they expand and they contract and expand because they're very essentially elastic when you're young. As you get older, they get stiffer. And so you can actually evaluate the stiffness just by the dynamics of that. And then there's vessels in the lungs. So these bright vessels are essentially veins going towards the heart at this point, right? They're bringing blood into the left atrium. So this is the left atrium here, pulmonary veins coming into the left atrium. And then that blood goes through the mitral valve into the left ventricle. So nice signal, looks pretty nice, right? Of tissue here. These are vessels. So some other, I don't know if these are still alive, these links, I hope they are, but it's really fascinating. Over the last decade, engineers take the skins off the scanner. This is the skin, right? Just boop, take it off, and then run the scanner. You can see this thing rotating and how much wind and everything it kicks up. So I would watch those if they're still up there. They're good videos. Siemens, always innovating, these folks. They put in 2 X-ray tubes on their force scanner and then 2 detectors. So it's like you have 2 CT scanners running in orthogonal directions all the time. So obviously that speeds up your data acquisition by close to a factor of 2, right? So you can essentially get an image every 66 milliseconds is their claim, right? Which is pretty cool. That's called the force scanner. This would be a movie on YouTube of this scanner with the skin off and rotating. And then we move into, in the last 4 years. Oh, sure.
You said like Siemens has like a narrow,
Z.
yeah, exactly,
Yeah.
narrow Z. But then that would be longer time.
Correct.
But then also the amount of electrons that are passing through the body would be less. So isn't that good?
Okay, so yeah, let me rephrase the question so it's on the record here. So the question is, if Siemens has a narrower Z extent of their detector, right? Then doesn't it take longer to make the picture? The answer to that is yes, it does take longer. However, what Siemens does is in the case of cardiac, they will take the EKG and they will assume that, say, three heartbeats are identical. And then they'll take the top of the heart, middle of the heart, and bottom of the heart over those three. And if they are truly identical, you piece those together and you get a very good looking heart. Okay. Now, if one of those beats goes wrong, then you get a terrible looking heart. You get something that has a chunk in the middle that's like shifted over or something. The other question is, given the fact that your slice is thinner, aren't you using fewer x-rays? And the problem there is you're doing it over three heartbeats. So you're doing it longer. Yeah, it's not a huge savings in x-rays. However, they would claim that when you take this narrow down data, the quality of that data is much higher than out in the periphery. And therefore, taking the risk of taking three heartbeats to get this spectacular image is worth it. And that's
Like, is it
so we've done studies where we've used a lot of Siemens data and studies where we've used a lot of GE data. The big difference is in the Siemens data, 10% of the patients you can't use because you get this, it's called step artifact. When you look at the heart, say in a transverse view, like a sagittal view, you'll see it's just distorted because the three beats were not the same.
So it's gonna rule of like 3 beats?
It depends. If you want higher resolution time, you can do 4 beats.
Okay.
Right.
Constant therapy. You have to check the patient first, right? Like
Yes.
what is for each patient.
Yeah. So you look at their EKG, how fast is their heart beating, and say, how, how many beats will it take me to spiral through this and get multiple time frames at each position? Okay. Much simpler to do it on a GE scanner because you're getting the whole heart at the same time. So you need one rotation, one heartbeat. And so if it matters, and where it does matter is if, say, you're doing a study where all of your patients are in atrial fibrillation, which we're doing right now, right? It's a nightmare if you have to get three beats that are same because no three beats are the same in somebody who's got atrial fibrillation, right? So you have that problem, whereas you want to get everything in one beat. So
Other than like cardiac, it will be fine. Cardiac. Okay, do we like a
Yep.
general application?
Well, should be. The other advantage of having a big wide detector, say in the lungs, if you were looking for some kind of dynamics, pulmonary dynamics, you can get them all at the same time, right? And then if you're doing perfusion, you can do it over a larger volume. So you just scan that volume, go. Whereas in Siemens, they do shuttle perfusion. So say you're doing perfusion of the brain, you can't do it all with one shot. You have to do one part of the brain, shift the patient, another part, shift the patient, another part, shift the patient, another part. So you go back and forth, done, 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 done. Okay, so my feeling is it's better to have the wide detector. Now, the images are probably not as good when everything works out well. So in the last few years, photon counting CT has become a commercial thing. It used to be just a research thing for about 20 years. Everybody knew how to do it. It was just like scaling it up such that you could do it on a commercial scanner and have it still be affordable. And so I've got a couple of things here. We're not going to spend a lot of time on it. There's a really good talk by someone who's a leader in this field online. So you can go see that. Also, one of the projects in 24 did a good job on this, so I've hooked up the YouTube link to that and where that talk starts. But basically, in conventional CT, which is what we've looked at thus far, you have X-rays coming in, they cause a flash of light, and then a photodiode essentially has a signal go off and say that's, a positive hit. And the size of that flash depends on the energy of the photon. But you basically integrate up all these flashes to get your signals. On photon counting, what happens is the X-ray comes in, and this is a semiconductor cadmium telluride, I guess. And what happens is the X-ray itself turns into electrons. Okay, so the electron cloud is proportional to the energy of this photon. And so that electron cloud then gets attracted right here to basically an anode, right? Which is such a little charged surface, and the electrons go right onto that charged surface. Okay. And uh, so it gets rid of crosstalk between these things. It gets rid of a lot of stuff that you have to get rid of with an anti-scatter grid. So if the energy is really low, you can just like filter out that photon. And it gets rid of baseline noise. You can filter that out, right? Just if it's not above a certain signal level, just filter it out. So it's not even there. Here, it's harder to do. And the big deal is you can make these little anodes very small, right? So unlike a light crystal, where if you make it smaller and smaller and smaller, the efficiency goes way down, the anodes can be really small, right? And so the detector elements get smaller and smaller, and the spatial resolution gets higher and higher on the picture. And so here's some examples. If you compare this with the image I just showed you, these are much finer detailed structures, right? This is like a really clear depiction of the calcium. And so you wouldn't, confuse yourself that the calcium is basically taking up the whole vessel. You can still see that there's things. So this is from that talk by Ron Blankstein. So you're welcome to go watch that talk. As the technology advances and we want to scan faster and faster, one of the things that you have to do as one of these manufacturers is you have to make an X-ray source that can make a lot of X-rays in a short period of time. So that's another thing that's occurred over this time of CT is just the power of the X-ray tube. So this is like an X-ray flashlight, and its power is getting stronger and stronger and stronger, so that now using these 120 kilowatt things, you can get enough X-rays in 150 milliseconds to make a picture. Because previously you would not have been able to do that, right? You had to have that X-ray tube on a much longer time. So you can look through these slides, but it's a comparison of the different manufacturers, their latest and greatest tube, the max power, the max voltage you can achieve, how the rotation, and the coverage. So here we're going to look at speed. So if you look at this EKG for this patient, they are obviously in AFib, right? Because if you look at the distance in time between the QRS complexes, it's like a random number around some mean, right? It turns out it's not a Gaussian around a mean. When you look at the R to R interval and you plot them as a histogram, it doesn't come up looking like a Gaussian. It has a tail, so it's weighted towards the long side. But anyway, we don't really know how long the heart rate's going to be, right? So if I took these three, so I took this, this, and this, they're quite different heartbeats, right? But if we can get everything done right here, all we care about is we capture this QRS, go to a constant time after it, and we know the heart's going to be in the same configuration pretty well, regardless of what rate it is. But if I look at this heart, it had all of this time to fill with blood. So after this beat, and I image here, all of this extra time is there filling, so the heart's going to be bigger. Then I do a quick ejection, and then I get my beat very quickly on. And so when I look at the heart here, it's not going to be as full. And so it'll be a smaller heart, right? And so if we can get everything done in one heartbeat, that gets rid of that problem. And that's when you get things like this, where this patient was in AFib, right? And but you can see the clarity. There's no sort of motion problems here. If you had 3 heartbeats here, that you'd be in a mess. Okay, so we'll look at the physics of X-ray attenuation just briefly. So if I have 1,000 X-rays coming out of my tube here, and they hit a sample in my CT scanner, let's say it's just 1 centimeter water or something like that. So it hits it, and you ask the question, well, how many X-rays get through? Depending on the attenuation coefficient, you look at it and say, oh, 800 got through. 20% were absorbed. If I put that same material right here, what's going to happen is 20% will get absorbed again. So I go down to 640. 20% again, go down to 512. If you plot that relationship, right? So it's a constant percent reduction per unit length of my sample because they're all made of the same material. That curve there has a very simple mathematical expression, and it's just whatever the start was times e to the minus mu x, where x is the distance that we've gone through. Okay. So it's just a mono exponential, right? And this, remember, this e to the minus mu x, we saw that in the equation before, and it was this one. A lot more letters now, but here's the I naught. That's the number of photons that enter the patient at this point. And then I multiply by the attenuation that occurs as I move through the patient from here to here. And so we'll call this 0, this point here, and D is at the detector, okay? And mu is the linear attenuation coefficient that is associated with this material. So if this is water, mu has a specific value. If this is aluminum, mu has a different value. If it's bone, mu has a different value. And so you just add up all of the mu's that you see as you go through fat, muscle, air, contrast, etc. So you just add all of that up, and that gives you the amount of attenuation. Here's our detector. We have it idealized here that we have a set of parallel beams of X-rays, right? We'll get there, but mathematically, we're not going to do that today. But if in the ideal situation, we have this parallel set of X-ray beams, and we have a detector that has an orientation parameterized by theta, and the detector element is parameterized by L along here. So I could go from 1 to say 1,000 detectors here. So my amplitude that I read out at this detector location and this angle or this projection is given by this, right? And that's our raw data that we're going to use to reconstruct the image. And this is a picture of that raw data at 1,000 different angles, right? So each time it's changing, that's a new angle. And so that's the raw data, right? Now, I think, did I put so our job is I have this data, which are these values, these brightnesses, and it's given by this equation. And our job is to go from those brightnesses because, I mean, I can look at those and I can actually see the patient and everything, but I want a 3D image of the patient. So it's to go from those brightnesses to this map, which is what is the linear attenuation coefficient at each point in the plane for this patient. And when I say in the plane, that means I'm going to do that analysis for, say, a line that goes through like this. That'll be one slice. And in that slice, I'll have XY coordinates, and I want mu as a function of XY in that slice. And I will do that, say, 256 times to get all of my slices. Okay. And so that's what we're going to do in each slice. We have this for the slice, and I'm going to convert it to this. And there's many ways to do that. You can do it with a big inversion, like a matrix inversion. Uh, you can do convolution back projection, which is exactly pretty well the same as what we did in nuclear medicine. Um, or you can do deep learning, right? You can do essentially an iterative technique where you use all of the underlying physics to get your best estimate of what the image is, and then you teach deep learning to go from that raw data to that image, right? Just do it 10,000 times or a million times, whatever it takes. So once it's done, we get pictures, and you'll see in the pictures and the data that you've got, the units of each pixel are called Hounsfield units, and they're basically numbers between -1,000 to 3,000, something like that. And the reason they did this, I think, in the early days is they needed to encode the image values as integers because the computers are really small, right? So you only probably had 10 bits to encode the values. And so they normalized all the values and came up with this unit called the CT number, or the Hounsfield unit. And what you do is at each location, you have a mu value estimate. And what we're going to do is we're going to take that mu estimate, subtract the mu of water for that scanner. And remember, we took that in the morning. We did the water phantom and the thing. So whatever the mu of water is in that scanner, we'll take that difference, we'll divide it by the mu of water. So it's a fractional change between your pixel and a water pixel, and then multiply by 1,000. And because this is a floating point number, right? And then air comes out as -1,000. We make that happen. Water comes out as 0, right, on this scale. And so we have between air of -1,000, water is 0. Then soft tissue is usually -100 for fat to about 60 for muscle, cortical bones 250 to 1,000, and metals up at 2,000, right? And contrast agent also very high. So if we look at this, here's a CT image. This is skeletal muscle between the ribs here, and the Hounsfield unit is 105. Fat is -120. This little bit of bone here is 750. The contrast agent that's in the myocardium is 650, myocardium 120. This little calcification, 1,300, right? So that's the clinical scale. And you can see here, this is a wire on the patient's chest. It's metal, and the Hounsfield unit is 5,000. So it's really, really high. So the magnitude of the Hounsfield unit increases if the X-ray attenuation increases. So those things that attenuate X-rays very highly get high Hounsfield unit numbers, okay? If you look down, so when we're looking at this, we can't really see what's going on in the lung because the Hounsfield units are way down at -800, right? So if we take our center and window and we go down to -800 to look at details down here around this, you can see that there's lung parenchyma, lung tissue, and it's not air. Air is -1,000, it's up here, but it's close to air, right? And these are the vessels that have contrast agent in them. Okay, so that's there. You can make a nice angiogram by just imaging those or rendering those vessels. Okay, we are at 10:45. Okay, I'm going to do this part first. So this is a direct inverse way of making a CT image. Okay, so remember our projections, we come through here, and it's the sum of the attenuation coefficients along that projection line gives us the raw data. So we're going to go here, and we're going to make the simplest image in the world, which is, well, maybe not the simplest. Simplest would be 1 pixel. This is a 4-pixel image, okay? So I have mu1, mu2, mu3, and mu4, and I have to figure out those values in order to make this picture. The data that I've obtained is P1, P2, P3, and P4. And that's if I shoot an X-ray through here, what is the sum of these attenuation coefficients add up to that, right? If I shoot it through here, the sum of these attenuation coefficients give me this. If I shoot it through here, that sum gives me this. If I shoot it through here, that sum gives me this. So I can write that down. That's just the physics of what we just looked at. I'm just adding up attenuation coefficients to get that G value. But we can write this down as a set of equations, right? P1 is just this, P2 is that, P3 is. So here you go. I've got data that I've obtained. I know these numbers, I measured them. These are the numbers I want to get to make my picture. So I just need to invert that system of equations, right? So I just write it out as you would in linear algebra, right? To just solve for these, given that you've got these and you know this matrix, right? This is like your scanner matrix or your control matrix. And those of you who are really good at linear algebra will look at this and say, well, wait a minute. This matrix isn't full rank. Remember rank? It's not full rank. I can write one of these as a function of the other three. So basically there's a dependency in there. So, P4 is P1 plus P2 minus P3. So I need to fix things. And the way I fix it is I take a different projection angle. I'm going to go through here and replace this equation here, right? Okay. So now I've replaced it with this. 1 and 4 gives me P5. So now this is a full rank matrix and I can invert it, right? And so you come up with an estimate of mu1 through mu4 just by doing a set of equations and inverting them. Now, what is the catch? The catch is if I have an n by n image, I have, if every mu gets a value and it's an n by m image, I have n squared unknowns, right? I also have n squared equations, right? And so if I've got a 512 by 512 image, I have 262,000 unknowns and that many equations. So my matrix is this size, 250,000 by 250,000 or something. So that's a really big matrix. Even on modern day computers, inverting that matrix is tough, right? You don't get a really stable solution if there's noise in there, which there is, right? Because these are estimates, but you know that your actual measurements have a little bit of randomness to them, right? So they're not purely noise free. You've got noise on these numbers. And so that's going to get you as well. So it's usually not done this way, right? It's usually done a different way. But the thing I love about this is it proves that you have enough data. If you take those projections, mathematically, you have enough data to do that, right?